In this video, we're going to take a look at a few more properties of the dot product. And just as a reminder, let me state the two formulas that we have now for computing the dot product. And again, I'll state the formulas for vectors in R3. So if we have V be the vector V1, V2, V3, and U be the vector U1, U2, U3, right? So we have the two vectors in component form. Then the dot product of U and V can be found algebraically by doing this calculation, multiplying the corresponding components. So V1 times U1 plus V2 times U2 plus V3 times U3. And this is the algebraic way, right? And obviously a pretty straightforward calculation once you have the vectors in component form. Alternatively, the dot product of V and U can be written in terms of magnitudes and angles. And so this is the magnitude of V times the magnitude of U times the cosine of the angle between the vectors. And this is the geometric way of looking at a dot product, right? So it's geometric. So basically, let me draw a picture that goes along with this. Let's say these are our two vectors. Let's say this one is V, this one is U. Then the theta is that angle, right? So we're going to talk a little bit more about this angle that's between the two vectors. And previously we looked at an example of how we could actually find it. So we could actually compute what this number is. But what if we wanted to know like what type of angle it is as opposed to its actual value, right? Now, remember the angle between the two vectors, the way it's defined is an angle in this range. 0 to pi if you're using radians, or 0 to 180 if you're using the degrees. So let's take a look at what would it mean about the two vectors if we looked at, just kind of get an idea of, as we range from 0 to 180, how are the vectors actually positioned, right? And then we will take a look to see, well, what does that mean about the dot product? So let's start, for instance, with when theta is equal to 0, right? Well, when theta is equal to 0, let's start with the sketch. So what that means is if the angle between the two vectors is equal to 0, then the two vectors have to be essentially pointing in the same direction. So let's say that would be U and that would be V, right? So the magnitudes might be different, but they definitely point in the same direction. Well, think about it. When theta is equal to 0, the cosine of 0 is 1. So this implies, in fact, I'll do a double implication because it goes both ways. The dot product, and I'll write it as U dot V. Remember that the dot product is commutative, right? So U dot V. In this case, if the cosine of theta is equal to 1, then it's simply the product of the two magnitudes, right? So like that. Yeah. So if the vectors have an angle of 0 between them, then the dot product is simply the product of the two magnitudes. Now, if the angle is acute, meaning between 0 and pi over 2 and 0 and 90 degrees. So if theta is acute, then what it means is they're not pointing in the exact direction, but they are, the angle between them isn't too big. So like this would be my theta, right? So if we have that, well, what we can say about the dot product in this case, right? Because obviously we're not going to be able to write down a relationship for every single theta, but what we can say is when theta is between 0 and pi over 2, the cosine of theta is always positive, right? So if theta is between 0 and pi over 2, then the cosine of theta we know is a positive number because it means the angle is in the first quadrant, right? But think about what that would mean for the dot product. The magnitudes are definitely positive because the magnitudes are represented by lengths, right? And these are two non-zero vectors, right? So this is a positive quantity, this is a positive quantity, and if we multiply it by the cosine of theta, which is now also a positive quantity, what it means is the dot product would have to be greater than 0. So sometimes you might simply want to know if the angle between the two vectors is acute. You might not need to know the exact value of the angle, but just to know, is it an acute angle, right? And the easy way to check is to compute the dot product and see if you get something positive, right? Well, let's continue going around essentially our unit circle, well, really the upper half of the unit circle. Well, what happens if our theta is pi over 2 or 90 degrees? Well, that means the vectors would form an angle of 90 degrees. So they would look like this. So that would be u, that would be v, and then this would be our theta. Okay, now obviously, so we can use the word perpendicular, but there's another word that is used quite a bit in the study of vectors and vectors that happen to form a 90-degree angle, and the word is orthogonal, right? So if theta is equal to pi over 2, then the vectors are said to be orthogonal, right? I'll go ahead and write perpendicular as well. So or perpendicular, right? That's what happens when the angle is 90 degrees. Okay, well, what does that mean about the dot product? Well, let's see, right? So, well, think about it. What's the cosine of pi over 2? Think about it on your unit circle. That's 0. So if the cosine of the angle is 0, it doesn't matter what the magnitudes are because everything's being multiplied on the right-hand side. So what does this mean? It means that the dot product is equal to 0, right? Pretty interesting result, right? So, and again, this is, in fact, of all the properties that we're going to refer to in this video, this one is probably the most important one. Whenever the dot product of two vectors is equal to 0, then it means that the vectors are orthogonal, right? So there's a direct, again, so orthogonality is a geometric concept. And obviously, this is an algebraic concept here, and they mean exactly the same thing, right? Or they are directly related, right? Then all we have left is to go, well, actually, we have 2 more to go. So what happens when our angle is strictly between pi over 2 and pi? That means the angle is now in the, let's say, the second quadrant. So let's say that this is U, and then over here now would be V, and this would be my theta, right? Again, when we're in this range, when theta satisfies this inequality, we can't really say something specific about like each and every one, except this. When theta is in the second quadrant, think about what your cosine value will be. Will your cosine ratio, will it be positive or negative, right? Well, if the angle is in the second quadrant, then the cosine of the angle has to be negative. And again, going back, looking at our basic relationship, geometric relationship between the dot product and the magnitudes and the angle, again, the magnitudes are always going to be positive, assuming our vectors are non-zero. And if now our cosine ratio is negative, then it means the entire product on that side will be negative. So this is the implication. This is the fact about the dot product. Whenever the dot product of two vectors is negative, then it means the vectors are, or I should say the angle between the vectors is obtuse, right? So this is, so theta is obtuse, all right? And then the last case now is, what about the other extreme? What happens when theta is equal to pi? Well, when theta is equal to pi, it means the vectors are oppositely directed. So like that would be U, and then V would be going in the complete opposite direction, right? So that would be our theta. Well, what's the cosine of pi? Well, the cosine of pi is -1. So this implies, right, that so in this case, our dot product, U dot V, will be the negative of the magnitude of U times the magnitude of V, right? So in a nutshell, what we have is a nice, essentially it's a characterization of the angle between two vectors, right? All the possibilities, and then how it relates, how each of these geometric properties relate to the dot product. And again, like I said, the really big one here is the fact that when the dot product is 0, then the vectors are orthogonal, or they meet at 90 degrees, right? Let's do an example just to wrap this up. Again, this will be a relatively short video, but let's look at an example. Well, actually a couple examples. Let's look at number 1. So are the vectors, I'll just write them down without even giving them a name. Let's say 2, -1, and 4. So are these vectors, let's say -4, 0, 2. So are these vectors orthogonal? Right? And part of it too is, like, when you have a question like this, and it's especially when they're three-dimensional vectors, and we've seen the challenge of sketching things in 3D, right, in 3 space. You don't want to rely on geometry, right, because your sketch would have to be very, very precise. And what if the components of the vectors aren't nice integers, right? We can't really rely on sketching. But if we're given 2 vectors and we want to know if they're orthogonal, what do? Check their dot product. So checking the dot product if I simply do 2, -1, 4, dot, -4, 0, 2. So now, since we have the components, right, we're going to use the algebraic form of the dot product. So this is 2 times -4 plus -1 times 0 plus 4 times 2. So this is -8 plus 0 plus 8. And our dot product is 0. So since the dot product is equal to 0, right? So since the dot product is equal to 0, the vectors are orthogonal. Right? The vectors are orthogonal. Right? And get used to the word orthogonal. It will be used several times in the future. So there's a nice little application of this. We don't actually have to compute the angle. I mean, now that we know that the dot product is 0, that automatically means that the theta is 90 degrees or pi over 2, but we didn't have to go through the process of computing it. The fact that the dot product is equal to 0, that tells me everything I need to know. Let's do one more example. So let's say, for what value or values of k is the vector k minus 3 comma 2, and I'll use the perpendicular sign here or orthogonal sign here. So this vector is orthogonal to this vector, -4 and then 2k plus 1, right? So we're told that the vectors are orthogonal, and we have to figure out what k is. Well, again, let's use the dot product. Let's set the, so the dot product So our dot product is, and so let's write it down. In fact, let me write the expression. So k minus 3 comma 2 dot -4 2k plus 1. And then that dot product, so it's the first component in the first vector times the first component in the second vector, so -4, plus the second component there times the second component there. And then let's go ahead and distribute and simplify. So we end up having -4k plus 12 plus 4k, and then plus, oh, I think, yeah, there should be a -2. Yeah, otherwise it doesn't work out well. That should be a -2. So this makes it a -4. Yeah, without that negative sign, the k's would completely cancel out. So, and then we have a -2, so like that. So the expression for the dot product is this, -8k plus 10. So the only way the vectors are going to be orthogonal is if this is equal to 0. So we're going to set the dot product equal to 0 and solve for k. So for orthogonality, -8k plus 10 must be equal to 0. So some simple algebra tells us that k has to be -10 over -8. Reducing that gives us 5/4, right? And you can always check. You don't have to, if the question asks you to state what the actual components of the vectors are, then you would plug your k back in. But the question really just asks for the value of k. So whenever k is 5/4, the dot product will be 0, and therefore the vectors are orthogonal, right? So again, a really nice use of the dot product to answer the question about when are vectors at 90 degrees, and is a simple property that the dot product has to be 0. See you in the next video.